Hello students, in this session we will discuss about Soliton-Soliton interaction and we will also discuss about the design guidelines of Soliton based links. Soliton-Soliton interaction, first we will discuss about Soliton width and spacing. We have discussed about the nonlinear Schrodinger equation which represents the Soliton, and this nonlinear Schrodinger equation holds good when the separation between the solitons are approximately there will be a good separation between the solitons. Then only the nonlinear Schrodinger equation holds good. To ensure this condition, soliton widths must be a small fraction of a bit slot, and usually in the case of communication purposes we will use the coding technique in return to 0, but in the case of solitons we will use return to 0 format. And in order to formulate an equation corresponding to the interaction between the solitons, let us see. If TB is the width of a bit slot, then we can relate the bit rate capital B to the soliton half maximum width TS, and that relationship is given by B equal to 1 by TB, and in this case TB can be replaced by TB equal to 2S0 into T0. So we will write the equation B equal to 1 by 2S0 into T0, that will be equal to 1.7627 divided by 2S0 into TS. So we have the equation B equal to 1.7627 divided by 2S0 into TS. In this equation 2S0 is TB by T0, and that represents the separation between the neighboring solitons. And next, the physical explanation of the separation requirement is that when solitons are very close to each other, there will be some overlapping between the solitons. So this overlapping creates a nonlinear interactive force between the solitons, and these forces may be either attractive forces or repulsive forces. That depends upon the initial phases of the solitons. Suppose there are different solitons which are initially in phase and separated by a distance 2s0, that is very greater than 1. Then the oscillation period for the soliton or the soliton separation is given by omega equal to pi by 2 into e raised to s0. The mutual interactive force between in-phase solitons results in the periodic attraction, or that may results into the collapse and repulsion, and the interaction distance corresponding to this interactive force is given by interaction distance, that is Li equal to omega into L dispersion, that is equal to L period into e raised to s0. This interaction distance usually expressed in terms of Li divided by L dispersion, and that will determine the maximum bit rate allowable in the case of soliton systems. So interaction distance is a main factor, and these type of interactions are not desirable in a soliton systems because they leads to the jitter in the soliton arrival times. So we have to avoid this soliton interactions. For that we are designing the soliton link, and one method for avoiding this situation is to increase the value of S0. That means we have to increase the value of S0 so that we can reduce the interaction between the solitons. Since the interaction between the solitons depends upon their spacing, if we are increasing the S0, we can usually avoid the interaction between the solitons. See, we have an equation B equal to 1 by TB, that is equal to 1 by 2 into S0 into T0, and this equation holds good for the values of S0, that is separation very greater than 3, and we can combine this equation for B, and also we have combined the equation omega L dispersion very greater than LT equations. Then we will get the equation for the soliton link as B square LT very less than 2 pi by S0 lambda all square into C by 16D e raised to S0, which is equal to pi by 8 S0 into modulus of B2 into beta 2 into e raised to S0. And this is the basic equation for the Soliton link design. And in this case, B represents the bandwidth, D is represents the dispersion, and lambda is the wavelength, and C is the velocity of the light, and LT is the total transmission distance. So, in order to design a Soliton link, the major important criteria is B square LT very less than 2 pi by S0 lambda all square into C by 16D e raised to S0, or omega L dispersion should be very greater than LT. So these are the basic conditions, that is omega L dispersion very greater than LT, where LT is the total transmission distance, and when omega L dispersion is very greater than LT, then there will be less interaction between the solitons. So this equation shows the effects on the bandwidth B or the total transmission distance LT for selected values of S0. That's all about this Soliton digital link design. Thank you.